Hi, Janice. Nice seeing you connected.
Hi, nice seeing you too.
It was pleasant to communicate, and thank you for sharing enthusiasm.
Of course, based off what you said in your previous email, let me see if I can find it again. Ah, I think I'll have to think on these a little bit more. I'll look at the papers again, but I'd have to think on each of these. But I'm particularly interested in the third and first one.
Hmm.
So,
We can make a plan. The third to be pursued during this summer class, and the first one would be very appropriate for the fall semester. Uh,
okay,
because right now we do not. Well, we need to talk more in details, and the first one is related to some derivation of equations, so it's a little more intellectually challenging. And number three and number two are more like following the procedure, so it's a little bit
okay,
more straightforward.
yeah, understood. Okay, awesome. Thank you so much.
Oh, my
Appreciate it.
pleasure, my pleasure, my pleasure. I think there is only two of us by now. I don't know if
It's kind of a bit odd. Typically, they're here by now, so it's interesting.
but I was receiving several emails from other class attendees. It seems they're considering class seriously and preparing homeworks and making some arrangements. So maybe it's just a little schedule thing.
Could be. Also, I do have to talk to you real quickly here about the presentation and everything. So, next week I will be quite busy. I have a um, previous appointment planned on the 6th around 9ish. I should be able to come to class, but I may have to end a bit early.
Hmm.
I'm not really sure, but I should be able to come to class then. The 8th, the 13th, and the 15th are a little bit up in the air as of right now, but it seems like we'll be able to do the presentation on the 13th. It's just the 8th and 15th that are a little bit iffy. So
Okay.
I'll tell you if anything changes. Okay.
Okay. Yep. And your subject for presentation that you have selected is quite simple. You may prepare it even during today's lab, and then even if you travel somewhere, you can connect, present, and disconnect. So
Okay.
it doesn't look
Gotcha.
okay. Uh,
Understood. Thank you so much. Appreciate
oh,
it.
my pleasure, my pleasure. Hello, Lihu. Nice seeing you connected. So we are waiting for a few more class attendees to join. Aha. Hello, Kristen. Nice seeing you connected. Thank you for the dedicated approach to the homework. So let's maybe look for a minute or two to check if there are more class attendees who want to connect now. And I'll probably send a little note to everyone that it is much better to use Chrome and Firefox. Okay. Okay, I think we will start anyway, and whoever is interested will look into the recordings. Okay, so we are going to do a little marathon over theoretical background and then go into the practical practical aspects. So it is a computational chemistry class summer version, which is a light version, a little easier than during the semester. The goal is to use theoretical background to write correct software on the right hardware and get characterized materials and compare them to experiment. Here are the links to recordings of the accomplished lectures, maybe not from this year, but from previous semesters. But generally, we do have 4 chapters for the theory background, and now we are at the beginning of the Hartree-Fock theory. So today we are going to get the main idea behind the Hartree-Fock theory, and then the rest will be a little easier. And in the practical aspect, which is the main goal of the course, so I'm going to flip back. At the end of each of the 4 chapters, there are presentations by attendees, and if you are attending the class, you are invited to present. The presentations are going over the subjects that we are going after the lecture material, some practical steps which are needed towards including computational component into your research. So in the second chapter, we do have these subjects that are listed, and in order to sign up, we are using this Google Docs address. So I am sending it just in case through the list. So among the class attendees, there are 3 attendees who already finalized the plans, and there are few more who are still deciding. So today we are going to cover the one that was, well, not everything related to orbitals, but the beginning of the practical steps for the orbitals, the subject that Janice has selected. Oh, hi you! Very happy to see you connected.
Yeah.
Very good. So today, after the lecture material, we will start doing my favorite subject, molecular orbitals. And Janice, probably if you just make screenshots of what we do today and put them into PowerPoint, you will be about ready to present. So,
okay.
So before we go to theoretical background, I will give brief overlap of the lab part, so that it will be not a surprise. So there are about three slides for practical things. By now, all of us were practicing all computations related to the class on the Photon server, and there the best part of it that one can run Gauss view graphical applications there. But in order to do more practical and advanced computations on the with Gaussian software, there is a server at NDSU, and if you have access to other servers with Gaussian installed, it doesn't matter, you can run it anywhere. But today I will do a short demonstration how the input file prepared on Photon with Gauss view can be transferred in a text form to a server and then executed there on the high performance computation. The main command is here, qsub. So some of you could be well aware of this arrangement. And after we quickly go over this job submission, we will return back to a Photon and we'll analyze the computation that we did last time for the simplest of the models for titanium hydroxide, and we will be looking onto so-called molecular orbitals. So the text commands will be those highlighted here, and then one will do a couple of mouse operated clicks in Gauss view for selecting the cube file and plotting contours, and as a result one will get the orbital, the colorful picture in the lower right. So the homework that I will try to design on Wednesday and ask you to submit by coming Monday, if we do not have Monday consult, so during the holiday weekend, will be to build several of such pictures for several models that you did. And those so-called molecular orbitals are very intuitive to interpret a lot of computational results. So summary, what do we expect today? Hello, Mahima. Hi. Nice seeing you connected. Did you got any helper assisting you?
Yeah, I got help from Muhammad, I guess.
Okay, thank you. Are you going to submit something like homework?
Yeah, so I need to work with the titanium dioxide one. So I tried that one.
Okay, yeah, please do. And for the research that you are doing on metal organic catalysts, I think it is quite relevant. Okay, so I will repeat things that I was telling before now. So right now there will be about 20 minutes of boring equations, but later on we will return to important practical things. So if you hate equations, just lean back and relax. I'll tell you when to wake up. If you love equations, you can concentrate. I just do not know how to go over this course without them, because we need terminology and stuff. So by the end of the meeting, we should get some idea about what is shown on this picture. So it is my ugly hand drawing illustration of an orbital with positive ions, and these hand drawn things are molecular orbitals. And we are going to accept to be not very scared by these two equations with big two curly brackets. And the meaning of these two equations is that we need to project multi-electron problem onto one electron problem. Okay, review what we did on previous meetings. So the goal of our meetings is to accept logical steps behind Hartree-Fock theory, and very approximately they can be symbolically mentioned through these boxes. So main concept is Slater determinant. Another main concept is mean field that we will cover today. And then, so we did spend additional meeting on spin concept and justifying Slater determinant. And in addition, so Hartree-Fock theory is a collection of ideas that several bright ideas that are formulated in as equations and then programmed as a software. It's not the most precise, but it is logical and important advance of civilization. So idea Slater determinant, idea of mean field, and later we will have idea 3, so-called variation theorem. And then through practicing the things, one is getting Coulomb and exchange electron-electron interaction, and then one is getting a procedure to compute electronic structure. So long time ago we did started consideration of a molecule as a collection of positive and negative charges, and building a Hamiltonian for a molecule that includes terms for total energy from kinetic and potential energy of both electrons and nucleus. But then we found an elegant way to throw off anything related to nucleus and concentrate only on the electronic problem. So we have kinetic energy of electrons, attraction of electrons to nucleus, and repulsion between two electrons. And the wave function with this Greek psi, it does depend on as many independent variables as many electrons we do have in a system. So it's 3 dots and then R sub n. And the main challenge in not only in this course but for the whole subject of computational chemistry is how to find this wave function, because wave function of many variables is challenging and not possible to do with even very modern computers. So one of the ideas is that one can represent wave function of many electrons, so one function of many electrons can be represented as product of many functions of one electron. But in order to match Pauli exclusion principles, it is not a simple product of this one electronic functions, which are like function 1 of variable R1, function 2 of variable R2. They are multiplied in the advanced form, so it is several products with different order with a few minus signs, and this order is called Slater determinant. Then we did briefly discussed that atomic wave functions for independent, for completely non-interacting atoms are good building blocks for solving actual molecular problem. And atomic wave functions do have 4 quantum numbers: orbital, principal orbital magnetic and spin is kind of rotating of charged sphere around itself in one or another direction, which is only analogy, is not quite correct, and there are 2 degrees of freedom. And if one converts this concept of spin into algebra, into a math, then one can introduce spin up and spin down as vectors with 1 or 0, like 2-dimensional vectors, which are 1 or 0, depending on whether this vector is with conjugation or without. It is either row vector or column vector. Typically, spin state is a superposition of this 2 basis states, which can be either bra or cat, row or column. And if in our experiment there are physical reasons for spin to be flipped, then one needs operators. So if wave function has 2 components, then operator is 2 by 2 matrices, and there are raising and lowering operators. So it is still a recite. We just try to recall what was done last time. Then, if one creates wave function of 2 spins with indices 1 and 2, so spin 1, spin 2, both of them can be up and down, and then for such state, the overall state will be combination of possible basis states, when first spin up, second is up, first spin down, second is down, first is up, second is down, first is down, second is up. And probabilities for each of these basis states have to be found in order to identify legitimate spin states. By finding eigenstates of the total spin operator, one finds that the best solution for this unknown coefficients, first, second, third, and fourth, is when first coefficient is 0, last coefficient is 0, and 2 cross coefficients are plus and minus 1 over square root of 2, which corresponds to superposition of up and down minus down and up. So by the form, this combination is resembling mathematical form of anti-symmetrized Slater determinant, which we use later on. Okay, so by now we have ended the review of previous meetings, and we are starting new material. So we are done approximately by here, and now we need to focus on so-called mean field concept. Okay, so what is mean field? Anyone can type or say. So mean is not like negative connotation, like it's not like adverse. Mean more like average. So I'm just looking on the list in the connection, and let me ask Janice, which thoughts do you have when you hear the word mean field?
I'm not particularly sure. I haven't learned about this yet.
So mean, which means average, and electrons repel each other, right?
Yeah.
So if we isolate one electron and then explore the average influence of the rest of electrons on our principal one, then the rest of electrons is like a box of average distribution of electrons that will exert some repulsive force on our selected electron. And it will be some average force. Average, mean, just a shorter word. Make sense? Good. Okay, I think we are done with the discussion. So here is the portion of the Hamiltonian for electron-electron interaction is in the atomic units, so we do not have any coefficients in front of this Coulomb term. All electrons have charge 1, therefore we have 1 here, and electron number I, position minus position of electron number J, summation, this will be interaction. So equations are boring and it's very natural for humans to hate them. Can we visualize this concept of mutual repulsions of electron by the mean field? So please follow me in the next imaginary experiment. Suppose we have a molecule, and here on the drawing, this ugly handmade drawing, it's like molecule of 3 positive nuclei. One can draw more, I just got tired. So we ionize all atoms that are present in our molecule in such way so that we have only positive nuclei. Now, let's return electrons back to this molecule, or to this strong ion. So if we bring in the first electron, it will try to distribute equally about each ion and form this red shape with maxima in the vicinity of electrons and minima in the gaps between electrons and 0 outside of a molecule. Please feel free to object or discuss if you do not like any of these concepts. So maximal density, maximal probability of first electron near positive ions. Now, what would happen if we throw in the second electron? So Janice already participated in discussion. Kristen, will the second electron come to the same spatial locations where first electron sit, or it will try to find some better place? Please type or reply if you have any thoughts.
The second electron is not superimpose on the first electron, but try and find a little some deposition.
Excellent. Excellent, super. So the Hartree-Fock theory is in how to say, is your natural thought. Basically, you formulated everything. The rest are just a little mathematical. So by the Pauli exclusion principle, second electron will take different spots. So here in my ugly drawing, it is this red shapes. Black shape. So the second electron will try to take spots close enough to positive ions, but far enough from the first electron. So it may take spots in between ions where first electron had minimum. It may form another shell around, but first and second electron will try to occupy different localization in space. And we can interpret it that ions, positive ions, attract second electron, but first electron repel second electron. And we need to take into account these both interactions. And this concept of the first electron repelling the second one in oversimplified way is basically mean field theory. So the Hartree-Fock theory is the mathematical way to take this concept in mathematical way. And if the wave function is expressed as product, then Coulombic interaction, Coulombic repulsion between these distributions of electronic clouds can be expressed as this Coulomb repulsive term in the center, and then products of this one electron wave function for first electron and one electron function of the second electron. So we will play with it a little bit more. So actual meeting starts right now, and the main idea that many electronic wave function with n electrons is so much to write and to think. Let's focus on only molecule that has 2 electrons. Maybe it's like H2 molecular hydrogen, but we will get some general concept that can be expanded everywhere. So product. First electron takes orbital number 1. Second electron takes orbital number 2. In case we do want to find total energy, we need to do some manipulation with our Schrödinger equation. Typically, a Schrödinger equation does have wave function, operator, and by acting with operator to wave function, we are getting the energy, eigenenergy, and then the same wave function, if wave function is a solution. But if you have a random wave function and only operator, there is a procedure that helps to merge together operator and wave function and generate an observable, the expectation value. Observable or expectation value. I was a little bit quick. Now let's play into the Wheel of Fortune. So guess which verbal construction is behind the yellow boxes. So which procedure allows to convert wave function and operator into observable. So Kristen knows it for sure. I'm even not asking her. Janice was already in discussion. Other volunteers. Would you like to guess what is behind the yellow box?
Actually, on my screen, I only see the slides review of 9 to 10, nothing else.
Thank you for the signal. Let me fix it quickly. I think I need to stop presenting and start presenting once again. Oh, if you see a similar thing once again, please let me know immediately, because it's okay. Now I think you do see this Wheel of Fortune, right? The game where one needs to guess the letters behind the boxes.
Yes.
So you may either guess the whole expression or just guess a letter.
I'm not sure.
Then just guess any letter from Latin English alphabet.
E.
Okay. Check. Yes. Zing. Ah, sorry. Okay, you got three credits for getting 3 letters correctly. So the letter E comes 3 times. Lihu, would you like to guess any letters or tell what is the whole word? You can type or tell if you have any ideas. Okay. Mahima?
I'm sorry, I have no idea.
Oh, okay. You can try any letter. I'll tell you if
W? Maybe.
W.
Sorry.
No W. Any other letter? Okay, if you come with the idea, please type. But thank you for trying. Mahima, do you have any letters to try? So tell or type if you have some. Okay, no ideas. Janice, would you like to guess the whole word or the letter?
I'll guess the letter. How about A?
Okay, that's a good guess. Zing. Zing. You got 2 credits for correctly guessing two letters. Any other letters you want to try?
How about P?
Zing. You got 1 credit more. 3 total. So
okay.
you has three letters successfully, and Janice has 3 letters successful. Anyone else wants to make a guess? Which one? Is it you? Who is speaking?
Oh, Kristen.
Oh, Kristen. V. Yes. Zing. Kristen got credit for correct letter.
So value.
Yes. U is getting 2 more, or value. So, and what is the first word?
Expectation.
Yes. And Kristen is winning. So Kristen is winning, completing the task. So expectation value is a procedure when one integrates wave function from the left and the right and placing operator in between. And we may want, so I'm very happy and with this little game, and hope that you did enjoy it. And now I'm going to be a little bit more serious. So there is an idea that is way above simple expectation value. So if you see here, we have wave function that is composed of 2 small 1 electron wave functions. And now we are going to do a crazy thing. So if one practices expectation value protocol, then one converts operator into a number. And we are going, so expectation point value converts operator into a number. But we want to do, I would say, partial expectation value, that it will be a number in respect to electron number 2, but it will be still an operator in respect to electron 1. So it's quite crazy thing. So we want to do partial conversion of operator into expectation value. And here it is implemented in the following way. So here is our wave function, and we multiply the whole equation by only second one electron wave function from the left. And to be symmetric, we do it here. Then if we plug it into the brackets, then inside the brackets we will get expectation values of kinetic energy of electron in respect to second electron, which will be like expectation value only of second electron, and then process all operators in respect to second operator. But the dependence on the first electron will be not resolved. So this will be not anymore operator for all electrons. It will be an operator that will affect only electron number 1, reduced operator. So this conversion from complete multi-electron operator to one electron operator is what Kristen expressed at the beginning of our lecture, when she told that second electron will try to find different spot in space. So all this reduced operator thing is just mathematical expression of this concept. So we are just getting partial reduced operator. And now there will be several boring slides, but I need to go over them. So if total energy of electrons is, kinetic energy of electrons is term for first electron and second, and we multiply this operator, we take Bra and Ket convolution over the second operator, it will keep the component for first electron kinetic energy unchanged, and there will be nothing for the second electron. So it will be operator in respect to first electron. And if we practice this convolution in respect to the remaining electrons, the remaining terms into Hamiltonian, there will be additional observations. So interaction between positively charged nuclei and negatively charged electrons, even in this H2 molecule, there are four terms, because interaction between two positive ions and two negative electrons, and 4 terms, 4 operators. If we carefully process them according to our convolution with wave function of the second electron, which we assume is known, then 2 terms will become numbers and 2 terms will become operators. So those that do have position of second electron in the denominator will become numbers. This convolution convert operator into number. And those that depend on position of the first electron will become partial operators. And the last term in the total energy operator, so repulsion between first and second electron. And here is the this thing is mostly pronounced. So we are averaging this Coulomb interaction in respect to the position of second electron, and one can write it down as integral dr2 phi 2 r2 absolute value square divided by absolute value r1 minus r2. So this integration affects only second electron, but it still will be operator in respect to the first electron. And this expression is core of the mean field concept and Hartree-Fock theory. So we need to practice patience maybe for very few minutes more. There are like 5 slides, but I will go over quite quickly. So if we have a full Hamiltonian and multi-electronic wave function, and then we may practice subtraction of all parts of the energy that are being converted from operator to energy form. And then we are going to move towards expression for Hamiltonian for many electrons, towards actual Schrödinger equation for one electron. And why I'm doing it, why I'm asking you to follow me? Because Schrödinger equation for one electron, it is what today's human society can do easily, even without computers. So from many electron Schrödinger equation, which is often unsolvable, we are moving towards one electron Schrödinger equation. So from total energy, we are subtracting kinetic energy of second electron, interaction of nuclei with second electron, and this will be like reduced energy. And we can do symmetrically the same trick for the second electron. And if we define this simplified reduced energy, that where we have removed everything related to second electron, here it is. And here we do have only things that affect as an operator onto electron 1. So this is operator in respect, operator for electron number 1. Here is wave function for electron number 1. Wave function for electron number 1. Electron number 1. And this is almost a success, or at least very important step towards designing Hartree-Fock theory. So this is one electron operator. This is one electron wave function, and it is what we know how to solve. This one electron operator is not quite independent. In order to build this operator, we already need to know where the second electron is sitting, the form of the second electron wave function. So it is not true operator in general sense. It is self-consistent operator, mean field operator. And if we symmetrically, I think it is will be last part of today's theory part. If we just symmetrically rewrite everything for the second electron, so we just swap first and second by places, then this one electron operator will depend on where the first electron has landed, and it will be literally the figure that we discussed at the level of cartoon. So first electron has landed. It does exert mean field through electron-electron repulsion. Therefore, second electron is taking different orbital. And this phi 2 of R2 is this thing, this black stuff. It is literally what we illustrate in this equation. So we are building an equation that helps to find phi 2, assuming that electron number 1 has already landed somewhere. So mean field of first electron determines Schrödinger equation for the second electron. Whew. So we are done with theoretical part. I do have several slides, but I think what we have is enough for today. Now, please open two windows in terminal if you're using Mac, or two windows in the mobile external if you're using Windows PC. So we are going over this practical things. So first, we will try to move the input file from the photon to Thunder and run the job there, and then we will return to photon and build orbitals. So I am going to bring the terminal here and increase the font so that it will be easy to watch. Bigger. Okay. So see, in your let me send an email with the okay. So if I am starting from scratch, I am typing SSH-y user at photon chem ndsu node.edu, and if you have access to other facilities with Gauss view and Gaussian, you can do it. So there I'm typing one of the keywords that was you already know, and please do not share and do not tell that you have it. So there I'm moving to scratch 001, then chem 476, then chem 676 summer, and then everyone should have a directory for his or her practice. So I'm going to my subdirectory and going to the subdirectory for today's lab 11. If I want to prevent system from disconnection for inactivity, I'm typing TLP. So there I do have I did inherited the files that were prepared last time, and I do need the one that is ending with .com. So we did create it with Gauss view. So I want a little disclaimer. The Photon server is just a little box on the table. It cannot do a lot of powerful computation, but there are a lot of computer data centers that have like 1,000, 10,000 CPUs and can do anything we want in the frame of class and most of things that we need to do for research. So one of them is called CCast, and I think Janice did instruct us during his presentation how to get an account there. So you are encouraged to use your accounts, and here just for training purposes I am giving an example of how I'm using mine. So the long login line is saved here. So user at name of the server. So, and then one types one of the passwords, one of the keywords that you should have. And if you have opened your own account, it has been communicated by system administrator to you. And after one is logging into the cluster, there is a disclaimer of available disk quota. So the home disk quota is quite poor, so 200 gigabytes is nothing today. The project disk quota is more reasonable, and we are going to use it. And if one needs to do some advanced storage for short time, there is a so-called scratch. So I'm going to Control-C, CD to the projects, going to CHEM676, and by now there is only one subdirectory. But if you are using your account, do things like that. If you want to practice for like one-time activity this account and you logged in with these credentials, please open subdirectory based on your name. And I will do the first part of demonstration with submitting jobs on the cluster very quick, because it is only a question of computational efficiency. And when we will go to plotting orbitals, I will slow down and check with everyone that we do it quick enough. Okay, so I'm going to the subdirectory, going to the I'll open another one so that we start everything from scratch. Web 11a, then going there, and now it is an empty directory, right? But I can type pwd and copy the path. Now I'm going to another tab where I'm logged into the Photon, and I am transferring scp the file that ends with .com, input file for Gaussian calculation, into user at host and then I'm putting column and copy pasting the path. So it is standard file secure copy. And then I'm typing the password. So practicing patience for a couple of minutes, couple of seconds, and then it did transfer the .com file. Now I'm making TOP to prevent log off due to inactivity, and going back to the tab on the CCast. There I'm typing ls-ot. Now it does have this file that has been created on the Gauss view. So you see here is the block for coordinates, and here it tells that we want to compute Hartree-Fock single point with Lionel 2DZ basis set. Now, practical step: copy bin small.pbs into here. Sorry, space period. ls-ot. Now I do have two files in the subdirectory. And one more step, copy this titanium blah 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 into input.com. So by now we have 3 files. So let's look what is inside this small .pbs. So this is a list of all parameters to interact between us as humans and the so-called job scheduler. So the supercomputing facilities typically have the front node with job scheduler and many like compute nodes that do actual jobs. And humans request a lot of things to do, and the job scheduler distributes jobs between available compute nodes. So if I type more small PBS, so there are several things, including the name, wall time. So here I'm putting 1 hour, and this is primary thing where one can modify a number of CPUs, 8, and one can put more if one needs to compute something advanced. And there it tells consider standardized name of input, standardized name of the output, and then it shows, it sets up path for all input and output file names for executable, and then does this G16, which is actual executable for Gaussian software. And then it shows take input and forward as output. So our input is input.com. So what I'm doing next is q sub small and hit enter. So it goes into the queue and types the number. So I'm copying this number of a job and type another command. We are almost done, and we will move to nice plotting of orbitals in few minutes. So I'm typing qstat, which is like state of jobs that are being in the queue, either running or pending. And then I'm doing grep and pasting the number of this job and hitting enter. And then it tells this job is about to start. So since there are much more users that there are here on this connection, it's a cluster for the whole university, there are many jobs, and it may take a little time before it will create the output. But if we need to do something productive for bigger jobs, this is the standardized way. And in a couple of weeks, we will use another supercomputer which is even more powerful. Okay, so and I did the same thing before class started. So when job is complete, it does generate file input.log, tail input.log, and it shows normal termination of Gaussian. So this is basically the same things as we did on the photon through clicking submit job with Gauss view. But here there are no substantial limits to size of the molecule and duration of the computation. It says access denied when I enter the password. Try the second one. I do not want to spell out or type passwords actively, but I will answer. Oh, I can answer to you through the. Oh, okay, Kristen, we're able to do it. Excellent. So, and after the job is done, EWD, I can. So, in order to avoid the log off for inactivity, I'm typing TOP. No, wait, just a second. If I type, let me show something. If I type qstat without any formats, you'll see ding, 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 ding. It shows how many jobs are being running. And what we submit is just a small fraction. So I'm going back to the photon, and there, so log period, and then I can download the results of the calculations back to the photon cluster, or I can do the same for the local computer. So SCP user at computer name path name of the file space. I didn't type it, and at the end I need to end with space period. So source and destination, space period, 1 period. Enter. And now it transfers input.log. So more input.log. And you recognize the Gaussian output that we were discussing last time. So this alpha eigenvalue, occupied and unoccupied, minus 0.5, minus 1, so about 13 electron volts. So one can, it ends with normal termination. So one can do the same things as we were doing on a local computer on the remote CCAST server. So please consider to practice it. Your knowledge and credit in class not depending on this, but when you will be doing your projects, skills like that will be helpful. I don't think I have. I will answer to you, Zheng, in the through the cell phone. I see your question, and I will type it independently of you. no, it's I'm almost done. So you should have enough information in the email to try it. So after we are, I'm rushing. I want to rush towards plotting orbitals, but please try to practice this transmission of input files into CCast, running jobs there and downloading back, and I will be individually helping to get through it. So now I am in the let me do a new directory, so I will do everything from scratch. Lab 11A. So previously I did some calculations in the previous lab on the local photon computer. So into here. So I'm taking all files that were processed last time. So from now on, please follow what I'm doing and try to repeat. I will try to be slower, and I will ask one by one if you are able to follow, and will try to help individually. So I did copy from the previous lab 3 files. The input file, which contains geometry and the request to compute single point energy with Hartree-Fock method and Lennard TDZ basis. Then log file, that it is a text file that includes the total energies of orbitals, so important characterization information in as a text. And then one more file, that CHK extension. So this file is not designed for humans. It is a file in the machine form, binary file, and you see that it is bigger. So this middle column shows the input file is 1000 symbols, the output file is 16,000 symbols, and this CHK is about million symbols, and they are not readable by human. It looks like garbage. But this file includes a lot of important information. And most important for us, it does include information about spatial distribution of electrons around ions. In the light of our lecture material, right now we are considering Hartree-Fock theory that connects positions of ions, settling of electrons into orbitals around them, and then forming many electron wave function all together. And while we are practicing the software for this Hartree-Fock theory, we can watch these intermediate concepts, especially the orbitals. We can watch how they are localized around ions. And this concept of molecular orbitals is broadly used in many areas of chemistry, not only computational chemistry. It's used in molecular orbital theory in organic, inorganic, and it is very intuitive tool to understand properties of molecules. So, as soon as you have these 3 files, and if you do not have these 3 files, please type or say to me. And practically, you can copy files from my directory to yours, because right now we shouldn't waste time on preparing these files. We need to learn how to analyze them. So when I'm looking through .log file, and we are coming through the list of orbitals that we were analyzing last time, let me do a little silly exercise and count how many orbitals are occupied. Oh, let me ask everyone, please type the answer. How many occupied orbitals are in model with single titanium ion? Mahima? You don't need to speak in the microphone. You can type if you see. Janice? I would count just like 1, 2, 3, 4, 5. Count. How many? 24. It agrees. If anyone wants to object, okay. Silence is a sign of agreement. Janice, you won. Everyone accepts your answer. So orbital number 24 is highest occupied, HOMO. Yeah, it was here. Yes, HOMO. And then orbital number 25 will be LUMO. So those orbitals number 24 and 25 are our focus, because occupied and unoccupied orbitals typically participate in optical activity. So this should be very close to interests of you. So if a molecule is able to be emitter of light, if it participates in photoluminescence, typically the emission happens from LUMO to HOMO. If the molecule is participating in a catalytic activity, it also bumps into like catalyst and reactant bumps into each other, and then they form temporarily shared orbitals between catalyst and reactant, but all this chemical activity happens near the band gap. So orbitals near the band gap are most important for optics and chemistry. So 24 and 25. Now, I do not count on my memory, and I did a little help for myself. More bin advice. Molecular orbitals. So this is a brief summary that one can go into Google and look for Gaussian manual. So all these little tricks are provided there. And basically from all this help, I need just first 2 lines. Instead of more, I will type have. So the commands form check and cube gen are automatically installed on any computer where Gaussian is installed. They are accompanying tools. So if we do have file that ends with CHK, form check is just analyzing, so I'm typing, and converting form CHK So I'm typing this command form chk space and then name of the output file that ends with .chk. So please try to practice this command. And I'm going to copy paste it into the common chat. Control C, Control V. So after you practice this command, there appears one more file that ends with fchk. So let me browse through all directories and see if .fchk file is available at your directories. Now I'll go through in reverse view. Okay, let's go to lab 10. Is it lab 11? Not lab 10, okay. ls minus rt head cd. Okay. ls dot chk. Just fchk. Are you logged into the photon?
I just connect to Thunder.
Oh, okay, okay.
Photon.
Okay. When you finish whatever you are doing, please practice this form check on the photon.
Okay.
So I did type the command in the chat line. And okay, good. Okay, I'm going to Joyanta is not connected today, so there will be no new files. Alicia also not connected. Okay, let's go to Mahima. Okay, Mahima, you do have CHK files. Are they from today? Yeah, today. So, would you like to try form check command? This shouldn't be challenging. So we have titanium with normal termination. I can type it instead of you, but then it will be not as interesting. Please type form check and then the name of the output file .chk. Hello, hello. Form check. Titanium 02 CHK. So I'm typing it instead of you, but please do it yourself next time. So form check titanium02.chk. And then after you do ls minus ot, you do have file that ends with fchk. Let's check Kristen. Empty. I'm working in lecture 10. Okay. LS-LT. CHK, FCHK. Excellent. Yeah, good. Thank you. And let's check into the. No. CD James. CD 11. T. FCHK. Excellent. Okay, very good. I'm returning back to my subdirectory. So next, beam advice on all goals. So next command will be cube gen. So the check and form check files contain a lot of information, much more than humans can analyze at once. But there is a way to extract useful information from there. Specifically, the command kubegen extracts information about molecular orbitals from the form check file. So I'm typing kubegen, then the letter O for orbitals, then telling MO for molecular orbital, number 24. So according to Janice, it will be HOMO. Then I'm typing name of the file that ends with FCHK, and then I type space and give the name of the file, of the output file. And it's very creative name, MO24, molecular orbital 24 dot cube. So why it is named cube? Because the space is chopped onto grid points with about equal amount of grid points along X, Y, and Z. And if one uses rectangular coordinates. So if there is a grid points arranged in space with equal sides, it corresponds to geometrical shape of a cube. So it is just a standard extension. When I hit enter, it thinks a little bit more. It thinks, and then it is done. And after that, I'm typing ls-ot, and there is one more file, mo24.cube. And you notice that it is a large file of about 7 megabytes. And we shouldn't look inside these files. But if you look inside, it is quite readable. It will correspond to numbers that humans can read, although 7 megabytes of text is a little too much. So I'm going to browse through the directories and check that you do have file with extension cube there. Mahima, did you try to generate this cube file? If there are some challenges right now, you may take notes and then ask your helper to do it, but it's critically needed. So do not postpone it. So what you were expected to do is to type cube gen space O MO equals 24. Then this tio2.f.chk, and then file name cube. And it didn't accept my command because I did a typo. So those are keywords that should be followed in a literal way. Okay, -LT. So now your directory has this MO24 cube. Later on, we can we will need to generate several more orbitals. Chase Web 11 MO2. Okay, yeah, thank you, very good. Lecture 10 -LT. F. So, Kristen, are you getting error messages? I do not see the molecular orbital file in your directory.
I'm doing an error termination message.
Okay, let me try to cube gen orbital. Oh, by the way, if it is titanium 4, the number of orbital will be different than in the single titanium. But no, I think it did work.
Oh, I want to try to type in something.
Those things are very sensitive, like case sensitive and space sensitive. So I just copy pasted. And if this is a model with 4 titanium, let's quickly look more. Control-C, Control-V. If you look through the file, it's huge. If you look, okay, we do not need all through the file of occupied. So the number of HOMO will be different here. So 5 per line. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 13 times 5, 65, and then one more. So 66. HOMO for this model will be 66. So we may generate orbital number 66 because 24 will be very deep in the valence band, and it may look beautiful, but it will not give insights into chemistry and physics of this molecule. And then practicing using. Yeah, I will be in your directory soon. -T. Okay. So in directory of Kristen, there are orbitals. Now let's go to the directory of U. cd rev 10 -lt head. Okay, I'm happy. There is an orbital. Very good. So Mahimat, Janice, Kristen, you. Okay. Now I'm returning back to my subdirectory. And there I need to open Gauss view, gview exe. I think I already opened it, so I am not typing it right now, but I'll type it in the common chat, gview.exe, and one can put the ampersand shift 7 at the end. So it's already, let me close it and do it from scratch. So now in Gauss view, I'm going to the directory where I'm working and go into File, Open. Then, if you look through standard log and out, you'll see one thing. But if you look through the file type cube files, it will navigate to your .cube file. So please do it, click on it and select it. So molecular orbital 24 .cube, and then click open. So you will see just boring molecule itself, but it does show geometry. The file includes additional information. I will show what to do in the Gauss view, and then I will give, we will look what to do for Kristen and you if Gauss view doesn't generate reasonable files. We will plot orbitals with other software. Do not worry, I remember about the things. So now go to Results and select Surfaces Contours. So after I click Surfaces Contours, there appears this sub-menu, and there will be option to modify ISO value. I will go to more details what this ISO value mean in the next theoretical part of the lecture, but the too small number will create ugly orbitals. It's better to increase this number a little bit, maybe 2-3 times, 0.6. And then I'm clicking on Surface Action and click on New Surface. So after doing this, there should be image like this appearing in your Windows. So please type or say if you are not able to generate it, because I cannot check it by looking through your directories. And if you are able to generate it, you may practice screenshot and copy it into PowerPoint or Word document, because it will be needed towards next homework. So I can perform all steps, but there is no image. Yeah, I will, Kristen and you, I will go over plotting it with on local computer through Avogadro. So, but let me try in the menu right here. Even if you do not see image, you can click Save Image File, and then Save Image File in the file, and then file name TIFF. I will just try several and then look which one is better. File name MO24 TIFF. TIFF is high quality, but it's too large. I don't know what it shows here. Oh, capturing image. Okay, maybe it takes. Save. Let me check if any files did create in the directory. Control C. No, it didn't create. Maybe because I was impatient, I did stop it. Let me try once again. Capturing image. Okay, maybe it tries to do it once again, or it could be too challenging, too large. Okay, 27%. It's probably it will work, but for Kristen and for you, but I will try and share more optimal and easy way. %. Okay. Let's check once again. No, not this. Okay, it did generate TIFF file that I can download. Okay, it's good news. And just in case, I can also try generating file, save image file, maybe in more like JPEG, which can be a little smaller. MO24 GPG. So I suggest that everyone who is listening and trying, please email me the images that you, if you are able to generate it, that you did on your own equipment. And I'm going to download the images created by this capturing image into local computer, check that they're visible, and then we'll go to opening this MO file with different software. pwd. So I'm edit, copy. So I am copying everything that starts with MO to the local computer. Into lowercase. Okay, and now before going into serious things, we will try in insert if the images were successful. Insert image from file. So JPEG was JPEG does work, and insert picture TIFF is also working. So I think it is important information for Christine and you. So even if you are practicing some Gauss view commands and they do not immediately show images on your screen, you can just make these clicks and save as image and then download it.
I don't think I can save it as image because when I save it, there's like error, failure, allocating memory for pixel buffer.
Okay.
Also attractive, or how does that work?
Yeah, try some other, and you may move, make the window for image a little bit smaller, so that it doesn't use so many pixels. But I
don't have.
Okay. Let's check if one can read and plot the orbitals on Avogadro on local computer. So it can read Gaussian formatted checkpoint, but I don't see Q if it takes Q. Okay. I do have a couple of backup solutions. Do not worry, because it is quite standard thing. Let's just copy everything. Okay, so how would it take form check? Aha, okay. So we need homo and then render. Do it want to do it? You? I think Vesta reads it right away. So
The second read the zip file.
Huh? The Vesta reads a cube file.
Okay.
And I think it is quite acceptable quality. Bonds new from titanium to oxygen. Okay, so Vesta does work. Let's check if the JMOL will be able to plot this. So okay. I never did it. I did it for the first time in my life, but JMOL is able to read orbitals. Very good. I think it's great. Okay, then even if Gauss view doesn't work, you are safe. You can do all research steps and all assignments. I do not know yet how to combine both atomic structure and the and the orbital, but it was able to read. Oh, okay. So I first read the log file and then the cube file, and it seems quite acceptable. Does it have the transparent? Kristen, does it resolve question for you? Were you able to download and open the orbital? Okay, okay, very good, very good. So, Janice?
Yes.
I bet on your equipment you were able to use Gauss view, right?
Yes.
But as a backup, you see that there are several pieces of software that do read these files and help to generate graphical information.
Yep, and they know how to read them through Avogadro too. So
very good, very good. So, do you have an idea how to interpret these orbitals? What and everyone is welcome to make comment. So, what are these spatial balloons? Like what do we learn and what do we see?
Electron clouds.
Yes, and we do have total 9 atoms, right? 4 oxygens, 4 hydrogens, and 1 titanium. Which atom these clouds sit around?
The oxygen atom.
Yes, yes. And what is the shape of these clouds? Is it like a sphere or 2 spheres or 4 spheres? There are clouds in the vicinity of each oxygen, and in the vicinity of each oxygen, what can you say about them?
P.
Yes, it is a p orbitals, and those are occupied, right? So it means that oxygen is electronegative, and it pulls electrons from titanium and hydrogen to itself. So it is very much expected that electronegative oxygen has most of the charge density, most of orbitals for the occupied orbital. Let me do a you do not need to follow, but I'll do a very quick demonstration. So if I generate orbital number 25, which will be unoccupied. Oh no, this is in the directory of Kristen. Here should be titanium. Okay. So if I generate orbital number 25, can you guess how the orbital should look like? Before before you see orbital, around which atom should be the maximum of the orbital number 25? Anyone has a guess? Who votes for hydrogen? Who votes that hydrogen will have no charge density around? Who votes for oxygen? No one wants votes for oxygen. Now let's so from the fact that no one voted for oxygen and hydrogen, it looks like everyone supports an idea that the occupied orbital number 25 should be around titanium, right? Please check if you see this trend. Yes, come in. So I will use just JMO now. So open the log for the model and now open the cube number 25. It looks like it is shifted in space, so it's not perfect. Let me. It's not as demonstrative. Let's do it. Doing Gauss here. Open 25. Results. Surface contours. MO isosurface 0.6. Surface action. New surface. So look at here. The unoccupied orbital is primarily localized around titanium, right? And it has the shape of d orbital with like four balloons. And if one places together these two images for occupied and unoccupied, one can get some intuitive chemical analysis of this molecule. That upon formation of the molecule, there is a charge transfer from metal to the surrounding ligand. So titanium is stable in the cation plus, right? 4 plus, which means it loses electrons. Oxygen is stable in minus, anion, right? And what we see here is an illustration of electron for occupied orbital. It is an oxygen, which means oxygens will be anions, and unoccupied is on titanium, which means titanium is a cation. So I think we are done for today. I will happily answer any questions, but if there are no questions, anyone is welcome to disconnect.
So I have questions.
Please.
So I didn't follow their comment. More being advised .mo.gauss. What does this command mean? It just creates CHK.
It is just it's a little note that I wrote for myself. So it is not a command of ghost view. It is what I copy pasted from the copy pasted from the manual and left it for myself. So if I forget the syntaxes, exact syntaxes, like where to put letter O, where to put the file name, I have a quick reminder for myself.
Okay. So for the form chk command is to form fchk file.
Correct. Yes.
What's the difference between chk and fchk file?
CHK is optimized for binary reading and writing. For like if suddenly there is a power shutdown in the middle of your calculation, but when power comes back, one can restart from the middle of the calculation. So this CHK file includes some intermediate information as computation is going on.
What is fchk?
And fchk is formatted CHK, so it is not for continuing calculations. It is for getting an output for humans to analyze the results of calculations.
Okay. And then cube file is for orbital.
Correct. One can also get a cube file for charge density, for electrostatic map, like which one needs for reactivity of a compound, and I will cover it on other meetings later.
Oh, so when we use a cube engine and click and then tap all means orbital. If we change all to others, then we have other information.
Yes, one can get another information. So.
Oh, okay, great. Yeah. Thank you.
Thank you. So we are done?
Yeah.
Okay, yeah. Have a good evening.
Have a nice day.
Oh, thanks, you too.